All right, I think we're going. Welcome to day 13 of C and Software Tools class. I didn't quite finish up the lecture 12 material last time, but I recorded a little video, probably 15 minutes or so of the material we didn't get to. So be sure to watch that. You don't need to have watched that before this lecture. I think this will still make sense, but sometime soon, I'd go ahead and catch up on the material we covered in that last little bit. It's mostly about function pointers. Today, we're going to talk about really a piece of the C language that we've been missing. If you like object-oriented languages, well, this is about as close as we get in the C language. We'll learn how to make structs, how to organize related data items together, kind of like the data part of an object. There are a lot of little topics that we'll talk about to try to make sense of structs. Questions before we get started today? All right. A struct, like I said, it's kind of like an object from Java, but just the data part of an object. We don't get to really make objects in C like we do in Java. It's not an object-oriented language, but we can group related fields together, again, like the data part of a class in Java. And in C, that's called a struct. In other languages, it might be called a record. It's just the ability to store different types of data in one thing. Here's the syntax for making a struct in C. So it's got the keyword struct. That's kind of like class in Java. That's kind of means something similar. And then a name for the struct. Here I'm defining a struct named person. And then inside curly brackets, as many fields as you want the struct to have. These are kind of like variable declarations. But every time you make an instance of this person struct, you get these three fields. So a person has a name. That's a struct. You can think of that as, well, it's a char array with 12 elements. So you could think of that as room for storing a string of up to 11 characters. And then a double field called height and a int field called age. So this looks kind of like a class in Java, I've said a few times. It's got that semicolon at the end, and if you're coming from Java, that's easy to forget. We'll talk about that more later and why that needs to be there. But a common mistake would be forgetting that, especially because if you forget that, the compiler will keep looking for that semicolon, and it'll probably complain on the next piece of code it finds because it was expecting the continuation of the struct. So if you define a struct and you forget the semicolon, you'll probably see that error a few lines later, wherever you have the next statement. So this defines a new type called person with these three fields. How do you use this? Well, it's kind of like an object in Java, except if you want to make an instance of this struct, if you want to make a person, you have to use the struct keyword. So you can't just say person and then, I mean, normally you would expect if this was a class in Java, you could say the name of the class and then the variable name to make instances of that class. In C, you've got to reuse the struct keyword. So to make a person, you have to say struct person, the name of the struct, and then any variable you want to make of that type. Unlike Java, you're not making a reference to a person here. When you declare a variable like that P1 there, you're going ahead and making an instance of person, and it's got the three fields we just defined. So when you make a person like this P1 at the bottom, you've already got a person, and it's got a name field and a height field and an age field. So here's how you make an instance of a person. You get a variable P1 that has these three fields. The way you access the fields is a lot like the Java syntax you're probably familiar with. If you made a person P1, then it has a height field, and p1.age is how you talk about its height field. So there I'm setting height to 1.75. I'm setting age to 24. And then the syntax I'm using at the top shows how you can put something in the two fields. The middle of this slide shows how you can get something out of the field. So if P1 has an age field, P1.age will let you store something in the age field. It'll let you get what's in the age field, and then you can print it out, or here I'm getting the height field and copying that to a variable. I can't do this with the name field, but that's not really because it's a struct. It's because name is an array. It's I think of it as a string, but it's really an array of characters. So you can't, and you already know you can't assign something to a whole array at once. So once I've made P1, I can't set its name field by just assigning to that. That wouldn't have worked with any array in C. So it doesn't work with an array that's inside a struct. So I can't do what I'm showing up at, same thing up at the top of this slide. I can't just assign a string to the name field. But you know other ways to do this kind of thing. You could write a little loop that copied the string a character at a time. You could use something like scanf to read input into that name field. So P1.name works just like any other char array. You could pass that to scanf and let it populate it with stuff read from standard input. You could use a function like string copy. P1.name evaluates to, well, it's an array of characters, so it evaluates to a char pointer. So you could pass it to any function like scanf that was expecting a char pointer. These would all be ways of putting a string in the name field. You could also use the initialization syntax. Once you've made a struct P1, you can't assign to its name field, but you can do it during creation of that variable using initialization syntax, and that's what I'm showing here. At the top of this slide, I'm making a person P1, or sorry, P2, and just like initializing an array, if as part of the variable declaration, I say equals and then inside curly brackets, I can list initial values for all the fields in that struct. I have to list them in the order of the declaration. So if you let me back up about 3 slides, right here, 3 slides. Well, for person, first I gave the name field as an array of 12 characters, and then height as a double, and then age as an int. So if I want to initialize them, I have to first give what needs to get copied into the name field, and then what gets copied into the height field, and then what gets copied into the age field. And then with this initialization syntax, P2, once it's created, it'll have these values in the field. If I didn't use up the whole name field, it would fill it with zeros, just like any other partial initialization. Questions before I try and move on? I see a couple of things popping up in the chat. All right, so this is kind of the short syntax for initializing all the fields in a struct. C99 introduced a more explicit syntax. When you initialize it like I'm doing up at the top of my slide, you kind of have to know the order of the fields. And if somebody changed that, then your code wouldn't work anymore, or at least you wouldn't be initializing what you think you're initializing. C99 lets you name the fields you want to initialize, and then you don't even have to worry about the order you initialize them. So if you say .age, even if that's not the first field, the compiler knows you're giving a value of 33 for the age field, and then a name for the name field, and then a height for the height field. And you can even mix the syntax for this. I wouldn't recommend it, but it behaves like kind of like arrays did. If you name a field and then you start giving values that you don't name, it'll just continue from the last field you named. This isn't a good example of that because the first thing I specify is actually the last field. But if you had started with .height and then you just gave another field after that, it would assume that age was next if you didn't say otherwise. Structs can be created in any of the 3 memory regions. They can be local variables in a function, so they could be stack allocated. They could be global variables. They could even be heap allocated. We'll see how to do that in a moment. And the initialization behaves just like you would expect based on where you allocate it. So here, if person P4 is a stack variable and you don't initialize it, then it starts out containing whatever was on the stack. It starts out containing uninitialized garbage if you do what I'm doing up here at the top of this slide. You can also do partial initialization, like you would expect with an array. When I make P4 down here, I'm only filling in its height field, but just like partial initialization for an array, if you initialize any of its fields, the compiler will fill in the rest of them, or it'll write code to fill in the rest of them with zeros. So I initialize height to 1.234 here. I didn't explicitly initialize age, but because I initialized some of the fields, age will start out with zeros in it. And this works however you initialize the struct. So for P5 further down, I'm only initializing its name field to ABC, but the other two fields will start out initialized to 0. In fact, the rest of that name field, it's 12 characters, I only gave it 3, but the rest of them will get initialized to null characters. And for P6, I didn't explicitly initialize any of its fields, but the GNU compiler still treats this as partial initialization. So this syntax will fill in all the fields to 0, even though I didn't really give any values for it. Questions before I go on?
What does the name get initialized to if you don't specify?
Down in this last example for P6, it gets initialized to zeros. So that whole character array would be filled with zeros. Since 0 is like a null term, it's the same thing as a null terminator. If you tried to print the name, it would show up as an empty string. And then the height and the age field would also get initialized to zeros. We'll see in a moment how you can think of a struct as being stored in memory. And then once we see that, you can think of this as, well, that just fills all of the memory for the struct with zeros. Any other questions, or if I missed the point of that previous question? All right, some new syntax. I made a big deal out of the semicolon at the end of a struct definition. For struct, we're defining a type, but I made the point that you got to put a semicolon at the end. That's only sort of true. The reason the semicolon is important is because in C, you can start making instances of the struct right when you define it. So here I'm making a struct called grade. I give it 2 fields. And I didn't put a semicolon right here. Without that semicolon, any name you put after that, any identifier, it's going to assume that you want to go ahead and make an instance of grade. So a grade is a variable of type grade. You can go ahead and start making variables. And you can even start initializing them if you want. So here I go ahead and define a type called grade. I make an instance of it. And I set it up so that its fields are 90 for minimum and A for the letter, which is kind of what you'd expect for an A grade. In fact, if you want to go ahead and start making instances of a struct, you may not really even need a name for that struct. If you can make all of the instances you need right when you're defining the struct, down at the bottom, I left out the name for the struct. I guess city or something like that might be a reasonable name, but I didn't bother to name it because the only instance I'm going to make is Raleigh. And I went ahead and filled in its latitude and longitude. So I can talk about Raleigh as a, whatever this struct is. I can talk about its dot latitude and dot longitude fields. I just can't, since I didn't bother to name the struct, I can't make any more instances of it. And this would be weird, although there are times when you need to define a type that maybe you're only going to use in 1 or 2 places. And if that's the case, this would let you define it without even giving it a name. We'll see an example later of where that is kind of useful. I mentioned this a moment ago. For structs, we can think of how they're organized in memory. And I want to remind you for arrays, well, an array is a bunch of things, one after another in memory, all the same type, So all the same size. So an array of shorts, like I'm making up here, you could think of as being one short after another in memory. A struct is a collection of fields. And at least for now, we can think of those as being laid out one after another in memory. So this person type we've been talking about, you can think of as storage for the name field, 12 bytes, and then storage for the height field, well, as a double, that would be 8 bytes on the common platform. And then storage for the age field, which would be 4 bytes on the common platform. So every instance of a struct is all of its fields one after another in memory. It's just they may not all be the same size. For an array, all the elements are the same size, but the struct has fields that could all be different sizes. So that's sort of the quick explanation of how a struct is stored in memory. There's one detail I want to introduce in this next slide, and that is the compiler may build gaps into your struct. This is called padding. And the compiler does this to satisfy what may be alignment constraints on your processor. Uh, this would depend on the compiler and it would depend on the processor. But some systems might be organized so that, say, a double can't start at an arbitrary memory address. Maybe doubles have to start in a memory address that's a multiple of 2, or maybe memory addresses that are a multiple of 4 or a multiple of 8. It would depend on the hardware and it would depend on the compiler. I say compiler because, well, even on a system where a double maybe could start anywhere in memory, maybe it's faster if you store a double so that it starts at an address that's a multiple of 4 or a multiple of 8. And the compiler may organize the layout of a struct to try to take advantage of that, to try to give you the fastest representation of that struct it can. Again, leaving little gaps could make it so that, well, let's take this example. If the name takes 12 bytes, if the compiler leaves a 4-byte gap after that, then the double field could always start at an address that's a multiple of 8. As long as the compiler, or sorry, as long as the struct starts at an address that's a multiple of 8. There's 8 bytes for the first part of name, and then 4 more bytes. And if I leave another 4 bytes worth of gap, then this double would start at an address that's a multiple of 8. And then the int would start at an address that's also a multiple of 8. I don't know if I said this word, but it's in red on my slide. Leaving gaps like that, or requirements that particular types start at addresses that are a multiple of a particular value, those are called alignment constraints. And there are a bunch of different alignment constraints that hardware might have. Some things might be required to be 2-byte aligned. That just means that they can't start at an arbitrary address. They have to start at an even numbered address. Some things might need to be 4-byte aligned. That would mean that they'd have to start an address that's at an address that's a multiple of 4. I guess the strictest alignment constraint that you would expect to see would be data that needs to be naturally aligned. And that means however big that type of data is, it has to start in a multiple of that size. So for naturally aligned data, an int could only start at a 4-byte boundary. That would mean it has to start at an address that's a multiple of 4. A double, if it had to be naturally aligned, would have to start at an address that's a multiple of 8. If you look on the common platform, backing up a slide, if you make this struct on the common platform and then you start looking at how it's laid out, sure enough, it will be laid out like my picture shows. The compiler will leave a 4-byte gap at the end of the name field so that the double field can be stored at an address that's a multiple of 8. Again, if the struct starts at an address that's 8-byte aligned, that's a multiple of 8, Then leaving that 4 byte gap would make sure this double also starts at an address that's a multiple of 8. And after this int, it would leave another 4 byte gap to do the same thing that we just talked about. If you made an array of these structs and you laid it out like this, then as long as this one started an address that was a multiple of 8, the one that comes after it in an array would also start at an address that's a multiple of 8. So the compiler does this typically to give you faster executing code. The processor that we're using on a common platform machine doesn't absolutely require that a double be 8-byte aligned, but it could be faster if it is. And unless you tell it otherwise, the compiler will lay out this struct like this, which means it's wasting a little bit of memory inside the struct. There's a little 4 bytes here that it's not even going to use, and another 4 bytes at the end that it's not going to use. If you knew this was happening, you could reduce the wasted memory, and that's another thing I'm showing here, by reorganizing the struct. If you swap the double field and the age field and try it on the common platform, it will lay out the struct like this. It can put the int right here, and then it doesn't have to leave a 4-byte gap. And then it can put the double right after the integer field, right after the age. And if you check it on the common platform, you can check this by asking the size of the struct. You can see you save a little bit of memory by organizing fields like this. So the compiler will keep the fields in the order that you ask for. It just may leave gaps between them. And again, those gaps are called padding. Questions before we try to move on? Again, the padding is there because in some cases the hardware might require it. That would be if the hardware had particular alignment constraints. Or even if the hardware doesn't absolutely require it, it may let the compiler write faster executing code. Structs. In C, structs support value semantics. We've probably talked about that before, and you probably talked about that in Java. To remind you, what do I mean by what do I mean by value semantics? It means you can assign between variables of a struct type and you get a copy. That's not how Java works, at least not for objects. You remember from Java, if you had 2 variables that referred to objects, they have what's called reference semantics. If you have a variable and you assign to another one, you don't get a copy of the object they referred to. You just get another way of getting to the same object. In C, when you define a struct, by default, you get value semantics for that. And that's what I'm showing off here. I define a struct up at the top. It's got a name field. It represents an event. So maybe the event has a name and maybe a starting time expressed in hours and minutes. There I make an event E1. I use initialization to fill it in with a couple of fields. And then I make another event E2, but I don't initialize it. But because structs support value semantics, I can do this assignment. Remember, you can't do this with arrays, but even after I've already made these 2 structs, I can copy from E1 to E2. E2 is a separate struct. I could change it later, but until I start changing it, it looks just like a copy of E1. It gets a copy of all of E1's fields. So you can use the value semantics offered by structs to copy between structs. You can't do this. You can't compare them. The language doesn't support that. It would be easy to have put that in the language. It just doesn't let you do that. So you can't ask if 2 structs have the same stuff in them, but you can copy between them. So that's kind of handy for copying one whole struct. The place where it really comes in handy is passing structs to a function. Since structs support value semantics, if you've got a function that takes a struct as a parameter, you can call the function and you can give it a struct, like let's say I've got an event E1. In the caller, well, that would mean I have a struct and it's got some fields in it. If I make a function that takes that struct as a parameter, and if you don't say otherwise, when you call that function, it gets a whole copy of your struct. Inside that function, you can access its fields. You could even change them. And then when the function terminates, the caller still has their struct unchanged because the function was just working with a copy. So unless you say otherwise, structs give you pass by value automatically. How do you say otherwise? How do you get pass by reference if you want? Fortunately, we already know how to do this. The same way we do pass by reference on primitive types. If you want to call a function and you want it to just use the struct you already have, you can pass that struct as a pointer. And I already mentioned this is what Java does automatically. If you make an object and you pass it to a method, the method doesn't get a copy of the object, it just gets to use the same object that was passed in. If that's what you want in C, and that is usually what you want in C, then you just have to pass the struct by address. And most of the time in C programs, when they pass a struct around between different pieces of code, they pass it by address, they pass it by pointer. Backing up a slide, you can still do this. You can pass it by value. It's just usually that's not what you want. Here, I've got another function that it does the same thing. It'll print out an event, but it gets the event by pointer, by pass by reference. When you call it, you give it the address of some event struct. You can see in the function definition, it says, I expect a pointer to an event. I promise not to change it. Notice we're using this const keyword that we talked about a few weeks ago. I want a pointer to some event struct, but I promise I won't change what's in it. So const lets us say that. Getting to its fields is a little bit trickier because dot works on values of a struct type, and E is just a pointer to a struct. So you can see syntactically, I take E, I dereference it, and now I'm talking about the thing it points to. Well, now it's a value of type struct, so I can use dot to get to its fields. I do need the parentheses there. If I didn't have them, well, we'll see in a moment, dot has higher precedence than pointer dereference, so it wouldn't mean what I wanted if I didn't have the parentheses. In C, it's so common to work with structs by pointer that this syntax is a little irritating. It's a little ugly, it's a little extra typing. If you've got a pointer to a struct and you just want to get to one of its fields, it's kind of unpleasant. Well, it's a little bit of typing to put in the parentheses and the star. So C has a shorthand syntax for this that people use all the time. And that's what I'm showing down, well, in the middle of my slide. If you've got a pointer to a struct and you want to get to one of its fields, well, you could do what we just used. You could take the pointer, dereference it, and then use dot to get to one of its fields, and that works fine. But that's what the arrow operator does automatically. It's made for going from a pointer to a struct to one of its fields all in one operator. It does the same thing that this slightly longer syntax does. Because, like I said, in C, you're going from a pointer to a struct to one of its fields so often. People use this arrow operator all the time in C. And that's what I'm showing here. This is the same print event function, but instead of using parentheses and dereference and dot, I just use the arrow operator here. So you could compare this to our previous version. They do the same thing. Once you get used to it, though, probably the arrow syntax looks a little easier to read than dereference, parentheses, and dot. Questions before we move on? This is how I'm going to access fields of a struct from here on, at least if I've got a pointer to that struct. We've actually been using two operators that we saw for the first time today. If you've got a value of a struct type, you get to use dot to talk about its fields, just like in Java. If you've got a pointer to a struct type, you use arrow. And both of these are in that highest category of precedence. They have higher precedence, kind of like anything that comes after the operand, like looking up a element of an array or calling a function. These are in that highest category of precedence. That's why we needed the parentheses before. Yeah, I don't know if I have anything else to say about that. Let's talk some more about value and reference semantics, because there's some more things that you could do with value semantics. Let's say instead of printing an event, we wanted a function that would read an event from a user. That's what this function does, read event. It makes an event struct, prompts the user and reads a name for the event and stores it in the name field. Notice I don't need an ampersand here because name is an array. And the name, even though it's a field of a struct, it's already passed by reference to scanf. So I can, when I use %s, I can just give it that array of chars that is the name field.
Would anything happen if you did put an ampersand there, though?
I think you'd, well, I'm not sure. I was about to say, I think you'd get a complaint for the compiler about type. I would say, since the name already evaluates to a pointer to the first element of the array, you shouldn't put it here. I'm not 100% sure you'd get a complaint from the compiler on that. But down here you need it. Hour and minute are both integer fields, even though they're hidden inside a struct. Once you get the hour field, you need the address of that int, same thing for minute. This fills in the struct, but if I want to give that back to the caller, I could return it by reference. Since structs support reference semantics, you can have a a function that returns a whole instance of an event. I got a picture over here that shows how you can think of that inside the function. You make an event and you fill in its fields. And then when the caller gets your return value, they can copy that into any event they want and then use that, that copy that they just made. But this could be expensive. You could, if you were copying structs all over the place, if the structs were non-trivial, you might spend a lot of CPU time just copying them around. You could make this more efficient with a little planning ahead, and that's what I'm doing here. How about if for read event, instead of filling in an event and then returning that to you, how about if the caller has to give me the event I'm supposed to fill in? How about if they need to make an event and they just give me the address of that event? Inside my function, I'll just take a pointer to an event, and then I'll do the same thing. I'll prompt the user and I'll read something into the name field and then the hour and minute field. But while I'm working on that event, I'm really working on the event they gave me. They passed me a pointer to an event, whoever the caller is, and then I just use that pointer to fill in its fields. This could be a lot more efficient than backing up what we were doing before, where we were filling in an event struct and then copying it at the end. This would save the copy. Having access to pass by reference and pass by value gives you more flexibility. You can choose what kind of semantics you want, but it also means you could make some silly mistakes, like what I'm doing here. You could implement read event like this. This version is almost the same as the previous version, just instead of passing a pointer to an event, how about if I pass it by value? Up here in the caller, I call read event and I give them the event I want them to fill in. But when I define the function, I take that event by value, which means I'm really getting a copy of the event. If I go in and change the name field and the hour and minute field, I'm really changing those in my copy of the event. And when I return, that copy is going to go away. It's just like a local variable inside this function, which means when I return, I haven't really changed the caller's struct. I was just changing my copy of it. And when we get back to the caller, their event 2 is going to look just like it did before they called this function. So this is a bad idea. I would say it's a bad idea because the function doesn't really do what it's supposed to. It reads stuff from the user, it changes an event struct, but all those changes are invisible to the caller. They all go away when the function returns. So this is a bad idea. Here's an even worse idea. How about instead of getting the event by reference, I fill in my own event and I return a pointer to it. That's what this version tries to do. Same idea. I'll make a function that reads an event from the user. So I made my own event here, E. I filled in, or I got with help from the user, I fill in its name field and its hour and minute field. And then instead of returning a copy of it, I just return the address of the event I just built. My type makes sense up here. I return the address of an event struct, and that's what I said I would do. I return a pointer to an event struct. The caller gets that pointer and they can store it in their own pointer variable. So type-wise, this makes sense. It's just a bad idea because you're returning a pointer to a variable made inside that function. Here, the event that you're returning a pointer to goes away as soon as the function exits. That's what I'm trying to illustrate here. Well, sure, the caller can get a pointer to the E variable inside this function, but that pointer points to something that goes away as soon as the function returns. So up here in the caller, if it looked at the memory E3 points to, it got a pointer when the function exits. It's just it points to a thing that's now gone. If you use that pointer, you'd be looking at memory that you're no longer permitted to look at. That was a stack variable, but no longer is on the stack. To do this, to make a function that worked like this, we would need to allocate memory that doesn't go away as soon as the function returns. And one way to do this is with dynamically allocated memory. Could we store one of these event structs on the heap instead of just letting it be stored on the stack? And then we could decide how long it stays around. If you'll let me back up a couple of slides, we already have one good way of doing this works just fine. We could have the caller give us a struct, and then we could fill it in, and that works fine. Backing up another slide, this also worked okay. It was just more expensive. We could return a copy of the struct by value after the function has filled it in. But what if we wanted the function to do this, to make a struct and give us back a pointer to it? We just wanted it to work. We wanted it to point to something that's still around after the function finishes. And like I said, heap memory would let us do that. To allocate a struct on the heap, we just need to ask for enough bytes to store a copy of the struct. And sizeof works just fine to tell us that. Here, I'm going to go to malloc and say, give me enough memory to hold however big this struct is. If you say sizeof, and then, well, the type for a struct is, for this struct, is struct event. However many bytes an event requires, this will allocate enough space for that. It'll return a pointer to it. And then we can save that in a variable of type pointer to event. I'm doing a typecast here. I don't really have to do that. But like I said a couple of times before, if I write my code like this, it'll compile just fine in C and in C++. Since C++ is a little stricter on types, I usually include this typecast, even though C doesn't require it. All right, so now I've got a pointer to dynamically allocated memory that's exactly the right size to hold an instance of this event struct, and it won't go away until someone else frees it. Since I've got a pointer to it, I can use it just like any other pointer to a struct. I've just got that memory through dynamic allocation rather than stack or static memory. So I could make a version of this function that worked with dynamically allocated memory in read event Same code, I just had to wrap it across a couple of lines. malloc space to hold a struct, fill in its fields via a pointer to that memory. Syntax here is a little bit ugly because I have to go get its hour field. I use the arrow operator to do that because E is a pointer to a struct. So this gives me its hour field. But for scanf, I need to pass the address of that field. So I'll put an ampersand in front. You don't absolutely need the parentheses here. The precedence works out the same way even without them. But I usually put them in here just to make this easier for a human to read. So I want the address of the hour field, the address of the minute field. Once I've populated all the fields in that struct, I just return that pointer to the caller. Since it's in heap memory here, the caller can use that pointer as long as they want. They just need to remember to free that memory when they're done. So now we know how to define structs. You can put as many fields in them as you want. And we know how to allocate them as local variables. We know how to allocate them on the heap. I didn't actually show code to statically allocate them, but that's easy. You could just make them as global variables and they would be statically allocated. Or if you wanted them scoped within a function, you could just put the keyword static in front like any other local variable in a function. Questions before we try to move on? All right, I want to show you another trick, and that is for making literal struct values. You won't use this a whole lot, but it's kind of handy when you need it. And to get at this idea, I want to remind you of how strings work, because strings have special syntax in C. If you want to make an array of characters, you can initialize it with a string. And what this says to the compiler is make me an array, fill it in with ABC123 and a null terminator to mark the end. So this would make a 7-element array that just started out with this stuff in it. But you may remember you can also do this, and this means something kind of different. Here, you're saying, I don't want an array, I want a pointer to a char, and I just want you to start it out pointing at this literal string in memory. So str2 would be a pointer. You're just saying the thing you want it pointing to. So go make me a string. You're saying to the compiler, make me a string that has ABC123 in it, and set up this to point to it. You ought to be able to do this with structs also. You ought to be able to say, make me a struct and put this in it, or make me a pointer and make it point to a struct that looks like this. And you can. You know that there's initialization syntax for making a new struct. And here I'm showing it for structs and arrays, because it's kind of the same idea. Here I'm saying make an array with these 3 ints in it, and this makes an array. Here I'm saying make a struct with this stuff in it, and this makes an instance of a struct. This syntax over on the right, the stuff I put in red, is the initialization syntax. And you can kind of think of that as saying, here's the stuff I want in my struct. Or on the previous line, here's the stuff I want in my array. But that syntax only works at initialization time. What I mean is down at the bottom. Here, you can't just call a function and say, make this array and pass it to the function. Now, that's the same syntax I've got up here. It's just, it only works when you're initializing a new array. Same thing with the struct. This sequence of values inside curly brackets, that only works when you're making a new struct. So even if E2 is another event, after you've already made it, if you're not initializing E2, you can't just say, oh, make me a struct with this stuff in it. Partly because if you made this array, the compiler doesn't really know what type the array is. And if you try to make this struct without the initialization syntax, the compiler doesn't know what type the struct is. But it does support a syntax that lets you do this as long as you tell it what the type is. And you've already seen this syntax for arrays. We talked about this maybe a week ago. we said there is a way of making a literal array that has particular values in it. You just put the sequence of values you want inside curly brackets, and you put what looks kind of like a typecast in front of it. Inside parentheses, the type you want in the array, and then a pair of square brackets. And that says, make me an array that has this stuff in it. The compiler can tell you want an array of ints because you had to say that in the type here. This syntax, and you already know this top syntax, this makes an array with these 3 values in it, and it evaluates to a pointer to that array. So this allocates the array on the stack. It just evaluates to a pointer to that array. There's a similar syntax for structs, and that's the new thing we're seeing here. Same thing, you can put the initialization syntax, and if you put the type of the new struct inside parentheses, this will make an instance of that struct, and it will evaluate to that new instance. So it's kind of like making a variable without even giving it a name. This makes a new instance of this event struct containing these 3 values, but it doesn't really give you a variable for that. It just gives you a value of that type. You can use it anywhere you would have normally used a value of a struct type. So you could pass it to a function. You could assign it to another struct like I'm doing here. The difference, or I guess one thing worth remembering, is in this top example. For arrays, this always evaluates to a pointer. So this says, make me an array with these 3 things in it, and evaluates to a pointer to that first thing, that 12. Down here, this evaluates to a value, not a pointer to the struct, but a value of that struct type. So you could use that to assign straight to another struct. It's kind of like a shorthand syntax for overriding all of its fields at once, if you wanted to do that. So it's just like, 10 would be a literal value for the integer 10. This is a literal value for a struct containing these 3 fields. We're about to use this syntax to work up a couple of examples. Questions before we start doing that?
Can you do partial initialization like this?
Yes. I don't know if I've ever done it. So in a sense, I'm guessing a little bit, but it seems like if this accepts the same initialization syntax, and I don't know for a fact I haven't done it, I just can't remember doing that, but it seems like you ought to be able to leave off these 2 fields if you wanted, and then you'll have those initialized to 0. Good question.
Can you make pointers using this?
Well, you can. So like if you put and we will in a slide or 2, if you put an ampersand here in front, you're saying make this thing, just give me a pointer to it. But keep in mind, this thing is still stack allocated. So if you say, I just want the address of it, you can use that address, but the thing that address points to is going to go away the same whenever this code goes out of scope. So even though this isn't really a variable with an ampersand, with a name, whenever you leave the nearest surrounding curly brackets, this stack allocated thing is not really safe to use anymore. But we will do that in a slide or 2. Other questions? All right, let's use this. So now I just want to show how you can nest stuff. So we've got 2 ways of kind of building aggregations of things. You can make structs to put in a bunch of different things of different types. You can make arrays to make a bunch of things of all the same type. And you can nest these. And we've kind of been doing some of this already. Name is an array, and we made it as a field for a struct. So no surprise, you can put arrays inside structs. And they work just like a local variable of a type array. Every time you make an instance of event, you get a name that's stored inside that event. This is kind of different from Java. Since arrays automatically have reference semantics in Java, if you made an object and you put an array in it, it's really a reference to an array. But unless you say otherwise, if you make an event and you put an array in it like this, every copy of that event has a little array living inside its memory. Oh, you can think of it as being organized like this picture in memory. Since name is an array, every event has a name field. If you had an event E and you wanted to get to its name field, it would be E.name. If E is an object or is a variable of type event. And then, like I started to say a moment ago, since name is an array, if you wanted to get to one of its elements, you'd put square brackets after name. What if you wanted to do this more Java-like? What if you wanted name to be more like a reference to an array? You wanted something like the picture I'm showing here. Well, the way to do that in C is with a pointer. There's nothing to keep you from making event, and name could just be a pointer to a char. Well, that would mostly work just like an array, but if you want to fill in a name, you have to have an array containing, we'll say, a string somewhere else in memory, and you would need to set up name to point to that. So if you built your struct like this, I would think of it as being laid out in memory more like this picture. The hour and minute field would just be ints stored inside the struct, but name is a pointer to an array that you got to find room for somewhere else. You could do that with malloc. You could use a literal string, whatever you need to, but declared like this is more like how Java does it. Name is a pointer to an array that could be allocated somewhere else. If you wanted to get to that name field, well, if you had an event E, and let's say E wasn't a pointer, it was a value of type event, then E.name would get you to that pointer. But you could still put square brackets right after it because you can already do that with pointers in C. This would go look up element 0 in whatever array is pointed to by name. And in this picture, that would give me the character W in this case. So these two slides, what we just did here was we showed how to put arrays right in a struct. And then every instance of that struct carries around that array inside it. Or you could do it more like Java does. Using pointers, you could have every instance of a struct carry around a pointer to that array somewhere else in memory. Like I said, you've just got to figure out where you're going to allocate that array. Here we're showing you could put arrays inside structs. You could make arrays of structs. So here it's kind of like we're putting a struct inside an array. A struct is a type. So you could make an array of that type. And here, that's one reason I picked the event example, because if you had a schedule, that would be like a list of events you wanted to make sure you attended. So here I made a schedule. You can read its type. It's an array of event structs. So every instance of it is an event struct. Here I'm filling in all of its elements. So element 0 is wake up at 6:30. Element 1 is breakfast. Element 2 is OS class. I'm not teaching OS this semester, but normally I do. Where were we? This is element 2. This is element 3. Using array initialization, I'm just showing off. I skipped element 4. But you can do that since it's an array. It's just the value you're assigning to element 5 is uses the struct initialization syntax. And here also, just to show off, I'm using the C99 syntax for initializing element 3 here. You wouldn't really switch syntax like that. The compiler can handle it. It's just, I wouldn't do that on a real project. Questions about this before I move on? I guess 2 more things I can say. I drew a picture over here that shows what you're building when you do this. You made an array of structs. So that array is one element after another, where every element is a little copy of one of these structs. So whatever it takes to build that struct shows up in element 0, and then element 1, and then element 2. The little white box here, I'm pretending there's some padding in that struct. Here I'm doing partial initialization of the array, so it follows the normal rules for that. I didn't say anything about element 4, but I initialized other elements, so element 4 is guaranteed to start out full of zeros here. And this array would have 6 elements in it. I didn't actually say how many elements, but that means for the compiler to figure it out based on the initialization expression. And 5 was the biggest element I mentioned, so 6 elements to store that. If you built an array like this, same array here. Well, it's an array of structs, each one that has fields. So if you look up a particular element of the array, like I'm doing down here, schedule element 2, well, every element is an instance of this struct. So to get to one of its fields, I use dot. So schedule element 2 is, it's this element OS class up here. So if you wanted to get to its name field, that would be dot name. If you wanted to get to its hour or minute field, you'd use dot. I'm making a big deal out of this because we could have made an array of pointers to structs, and we'll do that in a moment. Before we do, what if you wanted to make an array of structs, but you didn't want to allocate it on the stack, you wanted to dynamically allocate it? Well, if you're dynamically allocating an array, the right way to keep up with that array is via a pointer to its first element. So that's what I made here. Schedule is a pointer to an event. I'm just going to make it point to one of these structs in memory. I go to malloc to ask for enough memory to store not just one instance of an event struct, but 6 times that much memory. So I think, like my picture shows, that's like asking malloc to allocate enough memory to store 6 of these things, one after another in memory. Schedule is a pointer to the first one of those. But since it's an array, if I wanted to access one of its elements, that would be schedule bracket 0, let's say. And then since each of its elements isn't a pointer to a struct, it's a whole copy of a struct. If I wanted to get the name field out of element 0, it would be schedule bracket 0, close bracket, dot name. Again, since this is an array of values of the struct type, I use dot to get to its fields. As opposed to what? Well, this next example. Here, instead of making an array where every element is a whole copy of one of these structs, here I'm making it as an array of pointers. And I'm kind of really showing that in C, you can decide where you want value semantics and where you want reference semantics. For structs, they have value semantics by default. So if you want reference semantics, you need to use a pointer to that struct. And that's what I did up here. Now I'm making a schedule, but its type is different. Here, if you had to read its type, you would say, well, schedule is an array of pointers to event structs. If I had to draw a picture of it, it would look more like this. It's an array of pointers. Each one of them could point to a struct of this event type. I just need to make it point to one of those. And that's what I do with its initialization expression. This is the question someone asked before. They said, could you take a pointer to one of these? Well, that's what I'm doing here. I'm saying to the compiler, make me an event struct that has these 3 things in it. And then once you've made it, I don't want its value, I just want its address. So I put an ampersand in front of it. These are all stack allocated, which means they're going to go away when this variable goes out of scope. But as long as I only need them while I'm using schedule, that should work fine. And they'll automatically go away, which could be kind of nice. I just need to make sure I don't try to use those pointers after this variable has gone out of scope. I make 5 structs. I take the address of each of them and fill those in the elements of this array of pointers to struct. And I'm really building something that looks like this picture. An array of pointers, each one pointing to just one instance of this struct. But since this array isn't an array of event structs, and it's an array of pointers to event structs, the way you use those structs is going to be different. If you looked up element number 2 and you wanted its name field, well, this is an array of pointers. So element 2 of that array would be a pointer to an event. If you want the name field and you've got a pointer to an event struct, you would normally use the arrow operator. So schedule element 2 arrow name would give you the name field. If you wanted, name field is still an array. So if you wanted one of the characters in that array, you could put square brackets after that name to get to any one of its characters. Questions? All right, what else could we do? I guess the example I just did, we were pretending we were stack allocating that thing. What if we wanted to dynamically allocate it? Well, now we kind of like when we were dynamically allocating an array of pointers, each of them pointing to a row of an array. And we did that a couple of lectures ago. If we wanted to dynamically allocate an array of pointers, each of them pointing to a little struct, well, we might have to dynamically allocate the array of pointers, this column here, and that's what I'm doing on this first line. I want an array of pointers, each of them pointing to a struct, so I need to keep up with that via a pointer to the first thing in that array. It's already an array of pointers, so a pointer to the first thing would be a pointer to that first pointer, a pointer to an event. I go to malloc and say, give me enough room for 6 of those pointers, each of them big enough to store a pointer to one of these event structs. So this first call to malloc, I think of that as allocating space for this column of pointers. It's initially, it's uninitialized until I fill in those pointers, but that's what I do next. I loop through 6 iterations, going to the ith pointer and making it point to enough memory to hold an instance of this struct. I filled in each of these instances with a bunch of question marks because each of those, the way I've written this code, each of them is dynamically allocated memory. So who knows what it contains when I malloc space for that. What you'd typically do is you would fill in the contents of these events after you allocated them. I'll go ahead and say one more thing about this because I've seen people make mistakes. Normally, the way you would do this is you probably wouldn't allocate all of these uninitialized structs all at once. You would probably allocate this array of pointers, and then you would allocate these as you needed them. If you've got an array of pointers, each of them could point to a struct, but until you've made some events to fill it in, you're probably going to leave these pointers uninitialized. And then once you say, oh, I've got a wake up event, let's put that first. Well, that seems like the time to allocate the space for this and fill in this first pointer. And then if you had a eat breakfast event, once you've parsed that, you can allocate space for the next event and make this pointer point to it. There's nothing wrong with what I'm doing here. It's just not typically how you would do this. I've seen a lot of activity on the chat. Are there any questions before I try to move on? I'll look back at those chat questions at the end of the
I have a
lecture.
question, if that's
Sure,
okay.
go ahead.
What would ever be the use case for this specific syntax? Because
Oh, you mean why would you do it like this instead of like this?
Yeah, because we were saying in the chat that's horrifying and looks really easy to make mistakes. So
This picture?
yes.
Oh, I claim, so let me try to answer your question. I claim you do this all the time in C, although maybe I didn't sell it right. You probably wouldn't do what I'm saying up here. You wouldn't say, let's make a big array of pointers and let's make them all point to some freshly allocated structs. But if you believe what I said about how, well, normally once you make a struct, you don't copy it around a lot. You leave it where it is in memory, and then you just take pointers to that. Well, if that's what you're doing, then if you had a whole bunch of events that you were keeping up with, or a whole bunch of people in a class, or a whole bunch of data points that you were storing, you would probably keep up with them via an array of pointers, one of them pointing to each of those events. So even though, backing up a couple of slides, you can do this. You can make an array where every instance is a whole copy of a struct. That's not how Java does arrays of objects. In C, To prevent copying the objects around a lot, this is more typical of how you might do it. On your project 4, this is more like what you're doing. You're keeping up with a bunch of movies, and you're doing it by having an array of pointers, each of them pointing to a little movie struct.
Okay, so this is a lot more space and time efficient,
I
probably
would
as
say
well.
more time efficient. Space, whether you pack them all together or whether you store them separately and have pointers to them, it's kind of a trade-off there. I guess the advantage of this is you don't need one big piece of memory to store them all in one after another. You can have one of them here in memory, and who knows where the next one is in memory. You just have to keep a separate pointer to it to keep up with where it is.
Okay, thank you.
All right, I think I have one more example to show and then one more bit of syntax in C. I guess the last thing to say is, you can put arrays in structs, you can put structs in arrays, you can do all that by pointer. You can put structs in structs. And that's what I'm showing off here. To do this, I made my event a little trickier. I said, well, what if an event has a start and an end time, not just a start time? Now, those are both kind of the same type. So let's make a little struct for that. I made a time struct that has hour and minute, and then I put 2 copies of that inside event. If I had to look at how an event is laid out in memory now, it's more like this. It's got a name field, and then it's got a time that has hour and minute, and then it's got another end time that has hour and minute. So it's organized like this. Now an event struct has a name, a start and end time, which are both little structs themselves. So if I wanted to initialize those, I would put them in their own pair of curly brackets, because start is a little copy of a time struct, end is another little copy of a time struct. And since event contains start, which is a struct, which contains hour and minute, if you wanted to get to, say, the minute field of the event time, you would use dot twice, kind of like you would use it in Java. Once you've made an event, it has an end field, so dot end to get to its end field. And since end is an instance of a time struct, if you wanted to get to the minute field of end, it would be dot. If either of these were pointers, if event was a pointer to an event struct, then that would be an arrow instead of a dot. Or if these 2 guys, if start and end were pointers, then the second one would be an arrow instead of a dot. Like I said, I've got one more piece of syntax that I have missed. We haven't talked about this yet, but when I'm really writing C or C++ code, I like having access to type def. And Java doesn't have this. Java doesn't need it as much. But you've already seen in C, we can make some big, complicated types just by gluing together a few basic type operators, like arrays of pointers to functions that take arrays and return pointers to functions. And it takes a lot to say those types. And it's irritating if you have to say them over and over again. Typedef is a way of giving a short name to an arbitrarily complicated type. So you don't have to say that type over and over again. Typedef looks a lot like a variable declaration. In fact, when I'm in class, when I'm showing the syntax, and it's easy to get this wrong, which is why I'm making a big deal out of it. If you left off the word typedef there, so just read the rest of this line of code, it would be a variable declaration. You'd be saying, I want to make an int array named table that's a 10 by 10 array of ints. So without typedef, that's a variable declaration. If you stick the word typedef in front, it says, I'm not making a variable. I'm defining the name of a type. It'll have the name will mean the same type that variable would have had. So let me try to say an example of this. So without the word typedef, table would be a 10 by 10 array of ints. With the word typedef, table is a name for that type. So table means 10 by 10 array of ints. And you can use it like a type name from now on. Once you've defined it like this, and again, this isn't a variable declaration with the word type def, that name table is just a name for that type. You can use it like this. Table means 10 by 10 array events. So you made one of them here, you made another one here. This is kind of handy in C because it lets you write simple type names to mean types that would otherwise take a little bit of code to write down. You can use this for portability. Like if you needed the name for a type that was a 64-bit int. Well, the problem is on common platform, that's long, but on a different machine, maybe it's not. You could use typedef to have one place in your code where you said, I'm going to define a type named int64, and that's going to mean 64-bit int. And then everywhere I need a 64-bit int, that's the name I'm going to use. If I have to recompile my code on a system where that's not long, all I have to do is change this one line of code. And then everywhere I've used this other type name will automatically be using whatever the right type is for that. Like if I had to switch it to int or long or something like that, I only have to change this one line of code to fix that type name. For function pointers, this is kind of handy because it lets you give a short name to a complicated type. You remember in our previous lecture, we worked with a test function, and it was a pointer to a function that took an int and returned bool. Here I'm using typedef to give a short name for that kind of pointer. Without the word typedef, I'd be making a variable test function pointer that is a pointer to a function that takes an int and returns bool. With typedef in front, that's now the name of a type that does that. And if you wanted an array of pointers to functions like that, with a short name for that, it's easy to make that array. Now, test list is an array of 10 pointers to functions like that. So having makes it maybe easier to read the types of a thing without having to zigzag back and forth as much. For structs, this is awfully handy. Oops, sorry, one more example before we do structs. We came up with a couple of lectures ago how to make pointers to multi-dimensional arrays. And it was a little tricky. We had to figure out how, if we wanted to make a two-dimensional array, how to talk about a pointer to one row in that array. Well, if we had a name for a row of a multi-dimensional array, this would be easier. So that's what I'm doing here. I use typedef to say, oh, a row is a 20-element array of ints. So if you want a pointer to a bunch of rows, it's just a pointer to a row, and then you can malloc space to point to as many of those rows as you want. Without this, well, we could still do this. It just took code like what we've got at the bottom. Last time, or a couple of lectures ago, we learned how to do this, how to malloc space for a 50 by 20 array of ints. And then you can use that two-dimensional array via a pointer like this. It's just kind of hard to come up with the type for this. Again, if you had a shorthand name for a row of that array, the syntax gets a little easier. But like I started to say a moment ago, for structs, this is awfully handy because if you define a struct type, every time you use that type, you have to use the word struct to talk about it. But typedef would let you give a struct a short name, so you don't have to say the word struct over and over again. And people do this all the time in C. Up here, I'm making an event struct. Just like our previous examples, it's got a name field with room for a 9-character string and an hour and minute starting time. If I wanted to make instances of this, normally I'd have to say struct event struct. But if I typedef it to a short name, and that's what I'm doing here, this typedef says from now on, whenever I say event, I mean struct event struct. And now I can use event just like it was a plain old type name. I don't have to use the word struct every time I want to make this. because I already built it into what that type name means. So now I've got a short name. I don't have to use the struct keyword, and I can use event to mean that struct I just defined. Again, this is used all the time in C. I'm just about out of time. We've got 2 more slides left. Let me say this one more. This is, well, actually, I'm out of time, so I'll go ahead and stop here. We'll save these 2 slides for our next lecture. We'll cover them at the very start. I'll hang around if people have questions. Thanks for your attention. I'll see you on Wednesday of this week. Have a good week.
Thank you.
All right, I accidentally stopped sharing before I stopped recording.